Okay, in this video we're going to go over the review sheet for the final exam. So the problems that I go over on this video will be similar to the ones that will be on the actual final exam for my class, and you will have a help sheet with all the formulas and all the tables that you're going to need in order to complete these particular problems here. Alright, and problem number 1 is this: the data below represents the actual high temperatures for 14 consecutive days. Use the temperatures to construct a stem plot. Okay, now if you recall what a stem plot was back in chapter 2, usually a stem plot would have stems on the left-hand side and leaves on the right-hand side. So pretty much you're going to have a vertical bar that's going to go like this. And your stem will be based on the type of the data values where they start. And by looking at this, the lowest data value that I have is 50, and the highest data value is 87. So in this case here, my stem is going to start off with the number 5, then 6, then 7, and then 8. These stems represent the tens place, from 50 to 59, 60 to 69, 70 to 79, and then from 80 to 89. The leaves will be on the right-hand side of that vertical bar. And I put those leaves in numerical order. So for the 50s, I do have the following. I do have a 59, a 52, a 50, and a 58. So I'm going to start with a 50 because it ends in 0, so that's the smallest. So I'll put the leaf of 0 first. And then 52 will be next, and then 58, and then 59. So for 52, that leaf will be 2, and then for the 58, it will be 8, and then 9 for the 59. So that represents 50, then 52, 58, 59. And then for the 60s, there's only one number that's in the 60s. That's the 67. So that's going to be this number right here that I'm circling in. So that 67 will have a leaf of 7 for the 60s. And then for the 70s, I see 78, and I see 72, 77, and 71. Okay, and I'll circle these in red to show you the numbers that are in the 70s. So I'm going to start with 71, and then 72, 77, 78. So this is going to be 71, then 72, 77, 78. And then finally for the 80s, I have a lot of numbers that are in the 80s, like 81, 80, 85 twice, and then 87. So the smallest is 80, so I'll go ahead and write the 0 for the 80, and then 81. And I did say I have 85 twice, so with these stems, I have to account for each data value. So I have to write the number 5 twice, and then the last was 87. Okay, so this is what our stem plot looks like. Okay, so that's problem number 1. Number 2. Students participated in an experiment to test their ability to determine when 1 minute or 60 seconds has passed. The results are given below, and you have the 57, 53, 66, 69, and 52. And here we're going to find the following. We're going to find the mean, the median, the mode, mid-range, range, variance, standard deviation. Starting with the mean. The mean is always going to be the average of those data values, so that's represented by x bar, and that's the sum of all the x values divided by n. And n is the number of data values that you have. So in this case here, if I add the 57, 53, 66, 69, and 52, and divide that by 5. Okay, now, the numerator is just a simple addition. You add these 5 numbers together, you're going to end up with 297. And then 297 divided by 5, pretty much that's going to be the one decimal place. So 297 divided by 5 will give us 59.4. So the mean for that data set would be 59.4. Part B is finding the median of that data set. Now, before I find the median, I need to place these data values in numerical order. So, from smallest to largest, I'm going to have 52, and then 53, 57, 66, and then 69. Okay? Because it has to be sorted data values. 52, that should be 53. And then 57. 66 and then 69. Okay, so this is my data set in numerical order. Alright, next, the median. If you have an odd number of data values, that means the median is always going to be the middle number. Now, if you have an even number of data values, then that means your median is going to be the average of the two middle numbers. So here, I have an odd number of data values. There are 5 data values, so that means I select the middle number, which is in this case 57. So the median of this data set is 57. Now part C, you're going to find the mode. Now the mode is the number that occurs the most frequent. And in this case, each number occurs only one time. So that means there is no mode. No mode means that each number occurs only once. That there's no repetition of any other numbers in that data set. Now part D is the mid-range. Now to find the mid-range, we take the highest data value plus the lowest data value and divide by 2. So here the highest data value here is 69 plus the lowest data value is 52. I'm going to divide that sum by 2. So in this case here, 69 plus 52 will be 121, and 121 divided by 2, that's going to end up being 60.5. So the mid-range of that data set would be 60.5. Now part E is the range of this data set. In this case, the range is going to be the highest data value minus the lowest data value. The highest data value here is 69. I'm going to subtract from it the lowest data value, that's going to be 52. So if I subtract 52 from 69, I will end up with 17. So the range of that data set would be 17. Okay, and now part F is finding the variance of that data set. Now the way that we find the variance, I create a table. One column will be x, the other column will be x squared. And I'll go ahead and write down my data values that I have, and they don't necessarily have to be in numerical order. That's the 57, 53, 66, 69, and 52. And if I get the sum of these x values here, I can add these numbers up, and that would end up being 297. And I know that because when I found the mean, the sum of those 5 numbers was 297. Okay, so the sum of these x values is 297. Now I need to square each one of these data values. Okay, so when I do 57 and I square it, that's just going to be 57 times 57. That would be 3,249. And then 53 squared, that would be 53 times 53, which is 2,809. Then 66 squared would be 66 times 66, which is 4,356. 69 squared would be 69 times 69, which is 4761. And then 52 squared would be 52 times 52, or 2,704. And when I add these numbers up, that will be the sum of the x squares. So if I add these numbers up in this column, I would get 17,879. Okay. Now these numbers here is what's going to help me find out what the variance is, because the formula for finding the variance of a data set would be this. This is s squared, and that's equal to n times the sum of your x squares minus the sum of the x's, and that amount will be squared, all divided by n times n minus 1. And in this case, the n is going to be 5 because there are 5 data values here, so n is going to be equal to 5. So I just substitute those numbers into that variance formula. So n is 5. That's going to be multiplied by the sum of the x squares. That's this right here, 17,879, minus the sum of the x's, that's 297. But that 297 has to be squared. All that's over n, which is 5, times n again, that's 5, minus 1. And I'm going to simplify the numerator and the denominator separately. So in this case here, for that numerator, if I do 5 times 17,879 minus 297, and then if I hit that x squared button to square it, that numerator will be 1,186. Divided by, now 5 minus 1 will be 4. Then 4 times this 5 in front will be 20. Now if you wanted to, you can do 5 parentheses 5 minus 1, close parentheses. You'll see that it end up being 20 in your denominator. So if I take 1186, divide that by 20, I would get 59.3. So the variance of this data set would be 59.3. Okay. Now part G is the standard deviation. The standard deviation is just lowercase s. That's simply going to be the square root of the variance, which is your s squared. And the variance, we found that out to be 59.3. So if I take the square root of 59.3, and I'm going to round this off to 1 decimal place, it'll be 7.7. So the standard deviation for this data set is approximately 7.7. Okay. So all of that is problem number 2, parts A through G. Okay, now problem number 3. In a pre-algebra classroom, there are 11 boys and 4 of them are blonde. Also, there are 14 girls, 6 of them are blonde. What is the probability that a girl or a blonde child will be selected at random? Alright, in this case, we have to use the addition rule for probability. Okay? And that addition rule for probability, I'll go ahead and write this down. Is this: the probability of event A or event B occurring, because it's going to be a blonde girl, girl or a blonde child. So it's A or B. That's going to be the probability of event A occurring, plus the probability of event B occurring, and then we have to subtract off where we get a probability of event A and event B occurring. Okay, so in this case here, we're trying to find the probability that a girl or a blonde child has been selected at random, or will be selected at random. That would be the probability of a girl plus the probability of selecting a blonde. And then we got to subtract off the probability of selecting a girl and a blonde. So this is where we look at our table here that's given to us. Let's find the probability of selecting a girl. Well, here's the girl right here. The total number of girls is 14 out of a possible 25 children. So it'll be 14 out of 25 for the probability of selecting a girl. And then plus the probability of selecting a blonde. Well, here we go with blonde. The total number of blonde children would be 10 out of 25. So the probability of selecting a blonde would be 10 out of 25. And then we subtract off the intersection of a girl and a blonde. Well, by looking at this, here's the probability of a girl. That's this row. And the probability of selecting a blonde is going to be this column right here. So here, the intersection of the two would be that number where that intersection is at. And in this case, it's at 6. So the probability of selecting a girl and a blonde child will be 6 out of 25. That's the overlap that we have to subtract. And then we just go ahead and simplify this. Since the denominators are the same, we can do 14 plus 10, that's 24, minus 6, which would give us 18 out of 25. And then if we do 18 divided by 25, and on the exam you'll be required to write your probability values to 4 decimal places, this will be 0.72. And in this case, that's going to be 0.72, and then we add 2 zeros behind it. So the probability of selecting a girl or a blonde child will be 0.7200. That's problem number 3. Now problem number 4. Suppose a baseball player had 243 hits in a season. In a given probability distribution, the random variable X represents a number of hits the player obtained in a game. And this is the table that's given to you. So here, we're going to do parts A and B. In part A, you're going to compute the mean of the random variable, And part B, you'll compute the standard deviation of the random variable x. So in this case, here's what our table will look like in problem number 4. The first column will be your x, which is a random variable, and then p of x will be that corresponding probability value, and then x times p of x will be x times its corresponding probability value. And then x squared, you'll square each of your x's, and then finally you'll take x squared and multiply it by its corresponding probability value. So in this case here, that x will start with 0, 1, 2, 3, 4, and 5. And then p of x, I'll just copy down their corresponding probabilities. The next is 0.2512, then 0.1035, let's say 0.0338, and then 0.0200. Okay, I just want to make sure that I copied everything correctly, so that way. Okay. Now, for the x times p of x, we take the x value multiplied by its corresponding probability value. So if I do 0 times 0.0918, I'm going to get 0. And then 1 times 0.4997, that would be 0.4997. And then 2 times 0.2512, that would be 0.5024. 3 times 0.1035 will be 0.3105. And then 4 times 0.0338 will be 0.1352. And 5 times 0.0200 will be 0.1. Okay. And now for the x squared column, we just square each individual x value. So if I square 0, that's 0. 1 squared is 1. 2 squared would be 2 times 2, which is 4. 3 squared, 3 times 3, that's 9. 4 squared, 4 times 4, that's 16. And then 5 squared, 5 times 5, that will be 25. And then, for the x squared times p of x column, we multiply the x squared times its corresponding probability value. So if I do 0 times 0.0918, that's going to be 0. And then 1 times 0.4997 will be 0.4997. And then next, 4 times 0.2512 will be 1.0048. And then 9 times 0.1035 will be 0.9315. And then 16 times 0.0338 will be 0.5408. And then 25 times 0.0200 will be 0.5. Okay, so here my table is complete. Now I'm going to use that to help me find the mean and the standard deviation of the random variable x, which is parts A and B. So in part A, for a probability distribution, the mean is always going to be this. Mu is equal to the sum of x times p of x. So pretty much all you're going to do here is find the sum of this middle column right here where it's got x times p of x. You're just going to add those numbers together, and that will tell you what the mean is. And in this case, it's going to be 1.54 478. So here we're just adding these numbers in the x times p of x column to get 1.5478. Okay, now part B is finding the standard deviation. And that's going to be this. Sigma is equal to the square root of the sum of x squared times p of x minus mu squared. That's the square of the mean that we came up with in part A. Now, this last column, we're going to add these numbers together, that x squared times p of x column. We're going to add those numbers together. That's going to give us this part that's going to help us find the standard deviation. So if we take the sum of x squared times p of x, you're going to end up with 3.4768. And that's this part right here, the sum of x squared times p of x. Alright, in this case here, to find that standard deviation, that's going to be sigma is equal to the square root of the x squared times p of x, that's this part right here, that 3.4768, minus mu, which is 1.5478, and that's going to be squared. Okay, so that's this squared. And this can be typed into the calculator here, so if I do second x squared, 3.4768 minus 1.5478, and then hit the x squared button to square it, and then hit enter. And I'm going to round this off to 2 decimal places, so this will be 1.04. So the standard deviation for this probability distribution would be 1.04. Okay. And that's how we do problem number 4. Okay, now problem number 5. Notice that it's in bold print, so you'll be able to use one of the probability commands on your graphing calculator. It says here, assume that a procedure yields a binomial distribution with a trial repeated n times. Use your calculator to find the probability of x successes given the probability p of successes on a given trial. Alright, in this case, I'm going to do it on the TI-83 and the TI-84. Now here, you're told that n is 2, that that x is equal to 1, and p is 0.80. Now it yields a binomial distribution, so we have to use the binom PDF command. And the binom PDF command is always this, n times p times x. So in this case here, we're trying to do this, the binom PDF of n, which is 2, and p is 0.80, and x is 1. Okay, now if you're using the old TI-83 or the earlier version of a TI-84 plus calculator, this is what you'll have to do. Here we're going to do second and vars. And then you're going to go down to binom PDF using your down arrow key. Binom PDF, which is this command right here. Press enter. It's going to give you binom PDF with the left parentheses. And then you're going to be entering whatever n is. That's going to, and then it's separated by a comma. That comma is above the number 7. So it'll be 2 comma 0.80 and then comma 1 close parentheses, and then press enter. And again, we're going to carry this out to 4 decimal places, so it'll be 0.3200. Now, for those of you who have the newer version of the TI-84, like I have here, you're going to do second and bars, and then use your down arrow key to find Binomial PDF, which is this command right here. Press enter. Your screen is going to look like this. The trials is going to be what n is equal to, and in this case, n is 2. So you type in the 2 and then press enter. The p is that probability value, that's going to be 0.80, and the x value is, of course, the 1. That's what x is equal to. And then you press enter to highlight paste, and then press enter, and then press enter a third time. You'll see that it'll end up being 0.32. And here I carried it out to 4 decimal places, so it'll be 0.3200. So now the probability that x is equal to 1 would be 0.3200. Okay. All right, problem number 6. Assume that adults have IQ scores that are normally distributed, with a mean of 100 and a standard deviation of 20. Find the probability that a randomly selected adult has an IQ greater than 116. Okay, so this is one of those applications of a normal distribution, and that means we're going to need to draw a normal curve to get an illustration of what this is. Okay. So here I'm going to draw a normal curve the best way I can. I'm doing this free-handedly. I want you to know that. Here the mean was given to us as 100. The standard deviation was 20. That was given to us in the problem because we're assuming that it's normally distributed with a mean of 100 and a standard deviation of 20. So we want the probability that a randomly selected adult has an IQ greater than 116. So 116 will be over here somewhere to the right. And anything greater than 116 means I need to shade to the right. Okay. So I'm going to shade to the right of 116, which is right here. So that's the area that I'm looking for here. Now, for that x value of 116, I need to find out what z is. I need to convert that to an equivalent z value before I can use table A-2. So here, to convert to a z value, we do x minus mu divided by sigma. Okay. Now the x value is 116 minus what mu is, that's 100, divided by 20. Now let's do 116 minus 100. That's going to be that's just going to be 16. And then 16 divided by 20 to 2 decimal places, that will end up being 0.8. Well, 0.80 I should say, because our z value has to be to 2 decimal places if we're going to use table A-2. So your z is going to be 0.80. Okay, so this is where we're going to use table A-2 to get our area to the left. Okay. So let me get table A-2 out. and it's a positive z-score, so we have to look on the side of the table that says positive z-scores, which is this, and then find 0.8, which is this number right here, and 0.0 represents 0.00 represents the last digit or the second decimal, the number after the decimal point. So 0.8 and then 0.00, that value will be 0.7881. So the area to the left will be 0.7881. Now, that's not the probability of x being greater than 16. That 0.7881 is this area to the left. I want this shaded area to the right. So to find that, I have to subtract 1 minus that area to the left, 0.7881, which will end up being 0.2119. So the probability that x is greater than 116 would be 0.2119. Or in other words, that the probability that a randomly selected adult has an IQ greater than 116 would be 0.2119. Okay, so that's problem number 6. Problem number 7 deals with a confidence interval estimate for, I think, for a population mean. Yeah. Excuse me. Randomly selected students participated in an experiment to test their ability to determine when 1 minute or 60 seconds has passed. 40 students yielded a sample mean of 59.4 seconds and a sample standard deviation of 10.3 seconds. Construct and interpret a 95% confidence interval estimate of the population mean of all students. Alright, so let's identify what we already have here. We have 40 students. That's going to be your sample size. That's what n is equal to. N is equal to 40. It has a sample mean of 59.4. That's x bar. Standard deviation is given to us. That's going to be 10.3. And we're constructing a 95% confidence interval. And what that means is this. We need to find out what alpha is going to be. And that's always 1 minus the confidence level. And 95% as a decimal will be 0.95. So if I do 1 minus 0.95, that's going to be 0.05. We also need to find out what our degrees of freedom is. And that's going to be n minus 1. Your n, your sample size is 40. So 40 minus 1 would be 39. So here we got 39 degrees of freedom. And our alpha level will be 0.05. So here we're going to be using table A-3. And we always use alpha is equal to 0.05, and we always use it in 2 tails when we're dealing with the confidence level or confidence interval. And degrees of freedom is 39. That's what's going to help us find our critical t value, which is t sub alpha over 2. So here's table A-3. Now we're going to find 39 degrees of freedom. That's down here. Now, we got alpha in 1 tail and alpha in 2 tails. We always look under the row that says alpha in 2 tails. Here's 0.05, so we go down to where 39 is. And as you can see, that critical t value will be 2.023. That's going to be our critical t value, 2.023. And now we can find the margin of error, because the margin of error requires us to use the critical value of t sub alpha over 2 and multiply by s over the square root of n. S is your sample standard deviation, n is the sample size. Okay, so that critical t value, that was 2.023, times s, which is 10.3, divided by the square root of n, and that's 40. Okay, so here we can type all of this in the calculator, and I would carry my margin of error to 3 decimal places here. So, if I have, let's say, 2.023 multiplied by s, which is 10.3, divided by the square root of n, second x squared, or the square root, and then 40, and then hit enter. And to 3 decimal places, I will get 3.295. That would be the margin of error. And now I have my margin of error. I know what x bar is. I can go ahead and construct my confidence interval. So that confidence interval will be x bar minus e, and that's less than mu, and less than x bar plus e. That's the confidence interval for a population mean. Now x bar was 59.4. Minus the margin of error, that's 3.295. Then that's less than mu, and less than. X bar and e are still the same, but they'll be separated by a plus sign. So now if I do 59.4 minus 3.295, to 1 decimal place I'm going to get 56.1. So this is my lower limit, 56.1, less than mu, and less than 59.4 plus 3.295. To 1 decimal place, that'll be 62.7. And I'm rounding those limits to 1 decimal place because my sample mean is to 1 decimal place. Okay? So this is what my confidence interval looks like. Now I need to interpret what that confidence interval means. Okay? That's the confidence interval. So the interpretation for that would be that we are 95% confident that the true population mean for all students lies between those limits, 56.1 and 62.7. Now here you can just say, or if you want to be elaborate about it, you can say that we are 95% confident that the true population mean of all students who are able to determine when 1 minute or 60 seconds have passed falls between 56.1 and 62.7 seconds. Okay, problem number 8 is a hypothesis testing problem. Okay, just one moment. In number 8, it says here, simple random sample of 25 adults is obtained from a normally distributed population, and each person's red blood cell count in cells per microliter is measured. The sample mean is 5.29 and the sample standard deviation is 0.54. Use the 0.01 significance level to test the claim that the sample is from a population with a mean less than 5.4. Use the p-value method. Alright, in this case here, we're going to have to start off with the 8-step procedure for testing a hypothesis. So in step number 1, we want the original claim in symbolic form. And that's going to be, and we're testing a claim about a mean, so we have to use the Greek letter mu. And we're told that the sample is from a population with a mean less than 5.4. So this is the symbol for less than, and then 5.4. So the original claim is mu is less than 5.4. And now step number 2 is the opposite of the original claim. Well, the opposite of greater than, the opposite of less than would be greater than or equal to. So the mu is greater than or equal to 5.4. Then step number 3 is writing the null and the alternative hypotheses. One of these will be the alternative hypothesis, because the alternative hypothesis has less than, greater than, or not equal to. In this case, we have less than, so this must represent the alternative hypothesis. So the mu is less than 5.4. And that is the claim. The null hypothesis always has an equal sign in it. So it will be mu equals 5.4. So there's my null and alternative hypothesis. Now step number 4 is stating the level of significance here. In this problem, the level of significance is 0.01. So that's what our alpha level is going to be, 0.01. Now, in step number 5, we're going to calculate the test statistic. Okay, so the test statistic, well, let's identify what we're given in this problem here. We got a simple random sample of 25 adults, so that's what n is going to be equal to, 25. We got a sample mean of 5.29. The standard deviation was 0.54. Okay. And I'll go ahead and write down what mu is. That comes from the null hypothesis. So mu is 5.4. So my test statistic for a population mean is going to be t is equal to x bar minus mu divided by s over the square root of n. So here that x bar is going to be 5.29 minus mu, that's 5.4, all divided by s, which would be 0.54, over the square root of n. And n is 25, so it'll be square root of 25. Now, if we enter this in the calculator, you want to make sure that your numerator and denominator, well, your numerator is in parentheses, denominator is in parentheses, like this. And I'll go ahead and do this on the calculator so that you can see how this is going to be typed in. Here you do left parentheses 5.29 minus 5.4, close parentheses, divided by, and then left parentheses 0.54, divided by second x squared for the square root 25. Now, if you have the older calculator, you may have to close your parentheses twice. But if you have The newer ones, like I have here, with the screen looking like this, you have to use the right arrow key to get out from underneath the radical and then close your parentheses. And then hit enter. Now that test statistic, I'm going to round this off to 3 decimal places. So in this case, this will be negative 1.019. So my test statistic is a negative 1.019. Okay, now step number 6 is that in the problem you're told to use the p-value approach for this one. So here you're using the p-value method. You want to find what the p-value is. That's the probability of getting a test statistic that is extreme as the one that we've gotten from our sample statistics. Now the alternative hypothesis is less than, so that tells me I have a left tail test. So I know that my p-value will be in the left tail. And here's negative 1.019. That's to the left of 0. So this shaded area on the left would be my p-value. That's going to be my p-value that I'm trying to find. I have 2 things I need to find. My degrees of freedom, which is n minus 1. The sample size is 25, so if I do 25 minus 1, that's going to give me 24. Okay? Now, when we're testing a claim about a mean, we're going to do the TCDF command. Now, since it's a left tail test, the TCDF command to find the p-value will be this. Negative with 6 nines, and then followed by the test statistic, and then degrees of freedom. So in this case, my lower limit would be negative with 6 nines, comma, the test statistic, negative 1.019, comma, degrees of freedom. That's 24. Now I'm going to do it both ways using the graphing calculator for the TI-83 and for the newer TI-84 Plus. Let's start with this TI-83 Plus calculator. Do second vars, and then you're going to select the one that says TCDF, and it'll give you TCDF with the left parentheses. So here, this is where we enter this. A negative key, which is at the very bottom of the calculator, and then 6 nines, and then comma, which is above number 7, negative 1.019, comma, degrees of freedom, 24, close parentheses, and then hit enter. And to 4 decimal places, since we're going to round probabilities to 4 decimal places, that would be 0.1592. And now let me show you the one with the 84 Plus, the newer versions, because your screen is going to be a little bit different. Second vars, and then we'll select TCDF, which is right here, and then press enter. It's going to look like this. So your lower limit would be that negative with 6 nines. And then you press enter. Your upper limit would be that test statistic, negative 1.019, and then enter. Degrees of freedom, 24. And then you'll go down the page by pressing enter to highlight that, and then hit enter, and then hit enter again. And you'll see you'll get 0.1592. So that's going to be the p-value that you're looking for. That's going to be this shaded area here, 0.1592. Alright, now step number 7 is our decision rule. In this case here, we're comparing the p-value with our level of significance here. So the decision rule for the p-value will be this. If your p-value is less than or equal to the level of significance, which is alpha, you will reject the null hypothesis. Now, in this case here, your p-value, we found that out to be 0.1592. The alpha level from step number 4, or in the problem that's in problem number 8, 0.01. And when you compare those two, you'll see that 0.1592 is greater than 0.01. Okay, this is greater than. So 0.1592 is greater than 0.01, which violates our decision rule. So that means we have to fail to reject the null hypothesis. Okay, so we fail to reject the null hypothesis. So in step number 8, we need to write our decision rule. And of course, the wording of your final conclusion will be on your help sheet as well. So in this case here, the claim was the alternative hypothesis. We failed to reject that null hypothesis. So that means that there is not sufficient evidence to support the claim. And then we write out what our claim is. Okay, so our decision rule will, our conclusion will be this. There is not sufficient evidence to support the claim that the sample is from a population with a mean not greater than, less than. Okay. And it says so in the problem. So here we're dealing with a mean less than. .4. There's not sufficient evidence to support the claim that the sample is from a population with a mean less than 5.4. Okay, and that's all there is with problem number 8 with that hypothesis testing. Okay, problem number 9. Listed below are annual data for various years. The data are weights in metric tons of imported lemons and car crash fatality rates per 100,000 population. Using the critical value method, determine if there is sufficient evidence to conclude that there is a linear correlation between lemon imports and crash fatality rates. Use a significance level of 0.01. And here are the lemon imports, which is the first row. The second row is the crash fatality rates. Okay, so let's start off with this 8-step hypothesis testing procedure. So step number 1 is stating the original claim. And our original claim in that problem is that there is a linear correlation between the two variables here. So it has to be rho is not equal to 0. Okay? When rho is not equal to 0, that means that there is a linear correlation between the two. And then step number 2 is the opposite of the original claim. That's going to be rho is equal to 0. Meaning that there is no linear correlation between the two. Step number 3 is the null and the alternative hypothesis. The null always has the equal sign, so if rho is equal to 0, the alternative will always have the not equal to sign here. So we're always going to be dealing with equal to and not equal to. And that alternative will be your claim. And then step number 4 is our level of significance. In that problem, we're told to use a significance level of 0.01. And now step number 5 is where we use the graphing calculator to come up with our linear correlation coefficient. So we're going to use the TI 83 or 84 plus calculator. To find R. So here's our table right here. Now to enter these data values here, what we're going to do here is press the stat key. Select number 1 for edit because we're editing. We're putting in new data values here. Now if you have anything in L1 or L2 like I have here, let's start by going to L1 and then hit your up arrow key to highlight L1. Press the clear key and then press enter. That clears out all that data in L1. Same thing for L2. Use your up arrow key to highlight L2, press clear, and then enter. So L1 and L2 are cleared. Now I'm going to go back to L1, and in L1 I'm going to enter the data values for the lemon imports, which are these numbers on this top row. Okay, so here, I'm going to need to move this out of the way so you can see how I'm entering these numbers in. So here I'm going to type in 233 and then enter. 263, enter. 359, enter. 481, enter. 533, and then hit enter. You always hit enter after the very last data value. And then use your right arrow key to enter the data values in L2. So 15.9, 15.6, 15.5, 15.1, 14.7, and enter. Make sure you have the same number of data values in L1 as you do for L2, and each one corresponds to each other because these are paired data values here. 233 is paired with 15.9, 263 is paired with 15.6, and so on. Once we're done with that, we go ahead and press the stat key. Now we're going to use our right arrow key to highlight test. And then we're going to use our down arrow key to find the menu item that says Lin Reg T-Test. And that's this menu item right here, Lin Reg T-Test. And then press enter. X list should have L1, Y list should have L2. Frequency remains 1, not equal to 0 should always be highlighted. And then regression equation, that's going to be blank. Press your down arrow key to highlight calculate and then press enter. And now you want to find out what R is. So you see that arrow on the left hand side, that means that there's more stuff on this. So you're going to press your down arrow key all the way down to the end. So this is what R is going to be. R is equal to 3 decimal places, negative 0.968. So that's your linear correlation coefficient, negative 0.968. Okay. Now step number 6 is to use the critical value method. So here, with this, we have to use table A-6. We need to identify n. Now, in this data set, there are 5 paired data values here. So that means your n is going to be 5. And the alpha level from step number 4 is 0.01. So here, if we use table A-6, and go and find that. Okay, here we go. Table A-6 is this. We got 5 paired data. Alpha level is 0.01, so this is going to be your critical value, 0.959. So that critical value is 0.959. Okay, so that's step number 6. Now step number 7 has a decision rule that's different from all the other decision rules here for linear correlations here. If the absolute value of R is greater than the critical value, reject the null hypothesis. Otherwise, you'll fail to reject the null hypothesis. So here I need the absolute value of negative 0.968. And the absolute value of a negative is always going to be positive, so the absolute value of negative 0.968 will be 0.968. Compare that to our critical value of 0.959. Now comparing those two, 0.968 is greater than 0.959. So that's greater than the critical value, so that means that we can reject the null hypothesis. And then step number 8 is going to be our conclusion statement. So pretty much that conclusion statement, if we reject the null, that means that there is sufficient evidence that there is a linear correlation between the two. So we can say that there is sufficient evidence to conclude that there is a linear correlation between lemon imports and crash fatality rates. Okay, so that's the conclusion statement there. Okay, so all of that represents problem number 9. All right, and finally problem number 10. Okay, pretty much we're going to be dealing with regression with that particular problem. The data below shows the time intervals after an eruption to the next eruption of a certain geyser. And here you're given the height in feet, the interval after in minutes. In part A, you're to use your graphing calculator to find the regression equation letting the first variable be the independent variable, which is x. And then part B, find the predicted time of the interval after an eruption, given that the current eruption has a height of 114 feet. Use a significance level of 0.05. Okay, so the first thing I need is the regression equation. So this is actually number 10. Part A. I'm going to need the regression equation. Now on your calculator, they tell you that the regression equation is always going to be y is equal to ax plus b. So we're going to enter these new data values in as we normally would, like we did in problem number 9. So here, let me clear this out. We're going to press the stat key, and then we're going to edit. So we're going to select number 1 for edit, and I'm going to go ahead and clear out L1 and L2. And in L1, I'm going to enter the height. This first row right here, that's going to be your x value. That goes in L1. The interval after those data values will be in L2. So here for the height, will be 96, 128, 75, 128, 88, 73, 80, 96. And then I'm going to go over to L2 and enter the interval after. And I want to make sure that those data values correspond to the height. 66 and then 85, 59, 86, 70, 75, 73, 75. Okay, so here 96 does correspond to 75, 80 corresponds to 73, 73 corresponds to 75, and so on. And I have the same number of data values in L1 as I do for L2. Alright, next, I'm going to press the stat key. I'm going to use my right arrow key to highlight calc. The one I'm going to select is this one, linreg ax plus b. So I'm going to go down to that one and then press enter. Now, if you have one of the older calculators, it will give you the a value and the b value, but here it gives an extra step that you have to do here. You have to go use your down arrow key to calculate. You want to make sure x list is L1 and y list is L2, and then calculate. And there you have it. Now that a is that 0.322 to 3 decimal places, the b is going to be 42.865. Okay, so when we write the regression equation, that's going to be y is equal to, the a was 0.322, that would be your coefficient of x, plus the b, which is 42.865. That's the coefficient of y. No, that's your b. That's your y-intercept. Now, of course, it's going to be y hat equals to, we put this constant in front, and then the x term afterwards. So it'll be y hat equaling the 42.865 plus 0.322x. So that's your regression equation. That's going to be part A. In part B, we want to find the best predicted value, or the best predicted time of the interval after an eruption, given that the current eruption has a height of 114 feet. Use a significance level of 0.05. That tells me I have to do that 8-step hypothesis testing procedure. So step number 1, the original claim, we're claiming that there is a linear correlation between the two. So that's represented by rho is not equal to 0, meaning there is a linear correlation. Step number 2 is the opposite, meaning there is no linear correlation, so that means rho is equal to 0. No linear correlation. Step number 3, the null and the alternative hypothesis. The null has the equal sign, rho is equal to 0. So that means that the alternative will have to be rho is not equal to 0. And I'll go ahead and say that's going to be your claim. And then step number 4 is your level of significance. Now I believe that's 0.05, because they tell you to use a significance level of 0.05. So that's your alpha level. Now step number 5 is calculating that linear correlation coefficient R. Well, we've already got those data values in to get this, which is our regression equation. We can find out what R is from here by pressing the stat key and then right arrow over to test, and then use your down arrow key to find linreg t-test, which is this. Press enter. I'm going to go all the way down to calculate because X list is going to be L1, Y list is L2, not equal to 0 is always highlighted. Go to calculate. And then use your down arrow key to go all the way down to find out what R is. In this case is 0.778. So that's your linear correlation coefficient, 0.778. And now step number 6 is finding that critical value. In this case, we have 8 paired data values, so n is equal to 8. And that alpha level is 0.05. And that's where we use table A-6 to find the critical value. And that's going to be this table right here. So here we got 8 paired data values. The alpha level is 0.05. So that'll be 0.707. So that's your critical value, 0.707. And now we need to use our decision rule, step number 7. And in this case here, if the absolute value of your linear correlation coefficient, which is R, is greater than the critical value, we reject the null hypothesis. Now the absolute value of R, or the absolute value of 0.778, is 0.778. Compare that to our critical value of 0.707, you'll see that it is greater than 0.778 is greater than 0.707. That does satisfy our decision rule, so that means that we reject the null hypothesis. And then step number 8 is our conclusion statement. Now I'm not going to be elaborate about this one, but here I just say that there is sufficient evidence, since we rejected the null, that means that there is sufficient evidence that there is a linear correlation. Now, since there is sufficient evidence that there is a linear correlation, that means that our regression equation is a good model that we can use. So what we can do there is to substitute our value into that regression equation. So I'm going to rewrite the equation, y hat is equal to 42.865 plus 0.322 x. (0.322x). Now, in the problem, we're told that the current eruption has a height of 114 feet. So that's our x value. X is 114. So we substitute the x in with 114 into this regression equation. So we have y hat is equal to 42.865 plus 0.322 times 114. So we got 42.865 plus 0.322 times 114. Now I'm going to round this off to the nearest whole number, so that would be like 79, well, actually 80. Since our data values are to a whole number, so we'll round that off to the nearest whole number. And this will be 80 minutes. And that will be the predicted time of the interval after an eruption, given that the current eruption has a height of 114 feet. Okay, so this should be enough to assist you with that final exam, so hopefully you can watch this video as much as you need to prepare for that final exam. And do feel free to email me or call me or come by my office if you have any questions about any of the problems that are on this study sheet. Alright, thanks for listening and good luck on the final exam.